The outer solar system exists within a vast interstellar medium where sparse gas and dust extend across enormous distances and form a quiet but persistent environmental background. In this region, the density of matter is extremely low compared to planetary environments, yet particles move at high energies due to the relative motion between the solar system and the surrounding galactic flow. High-energy cosmic particles travel through this space, continuously originating from distant supernova remnants, active stellar regions and energetic galactic processes that shape the broader environment. Although the interstellar medium appears empty on human scales, it contains enough material to influence radiation propagation and the long-term evolution of particles moving through the solar system's outer boundary. At the edge of the solar system's influence, the solar wind weakens and gradually merges with interstellar gas, creating a transitional region where charged particles are redistributed and redirected by magnetic fields. This boundary is not a sharp wall, but a layered interface shaped by pressure differences between outward solar emission and incoming interstellar material. Within this interface, energetic particles experience gradual slowing, scattering, and deflection, producing subtle changes in their trajectories over vast distances. The environment remains stable over short time periods, yet on longer astronomical timescales, it responds to variations in solar activity and galactic conditions that shift the overall balance of incoming and outgoing particle flows. Some particles, originating outside the solar system, carry sufficient energy to pass through this boundary region, with minimal interaction continuing inward toward the planets. Over time, this continuous inflow contributes to a background level of radiation that remains present throughout the solar system even far from the Sun. The interaction between interstellar particles and the solar wind also produces regions of gradual heating and rarefaction, where local conditions shift slowly as different streams of matter overlap. These processes occur on scales far larger than planetary orbits, extending across distances that take years for light to traverse. Despite the apparent emptiness, the interstellar medium plays a key role in shaping how radiation and matter move into and out of the solar system. Particles entering from this region can carry signatures of distant stellar explosions, preserving information about processes that occurred millions of years ago. Over long durations, the cumulative effect of these incoming influences contributes to a subtle but constant reshaping of the solar system's energetic environment. This outermost layer of influence does not behave as a uniform medium, but instead fluctuates as the solar system travels through different regions of the galaxy. Such fluctuations alter the density and energy of incoming particles, creating variability in radiation exposure over extended periods of time. Even though these changes are subtle, they accumulate across vast distances and long timescales, shaping the background conditions experienced throughout the heliosphere. The heliosphere itself acts as a partial shield, reducing some of the incoming galactic radiation, but never fully eliminating its presence. As a result, the interstellar boundary region remains an active interface where external and internal influences continuously interact. Over millions of years, the solar system's passage through varying interstellar conditions produces gradual shifts in this energetic environment. These shifts are not abrupt, but emerge slowly as large-scale galactic structures influence local particle distributions. In this way, the outer solar environment is continually shaped by forces extending far beyond the Sun itself. High-energy particles arriving from distant astrophysical sources contribute to a persistent background of radiation that permeates this boundary region. Their interactions with sparse gas atoms produce secondary particle cascades, which gradually dissipate across space without forming dense structures. Although extremely rare on any small scale, these interactions become significant when considered over the immense volume of interstellar space. This persistent low-density environment establishes the baseline conditions into which the solar system continuously moves. As the solar system travels through the galaxy, it experiences subtle changes in this interstellar background that influence long-term particle behavior. These influences remain largely invisible to direct observation, but are inferred through measurements of cosmic radiation and particle flux variations. Together they define a dynamic and constantly evolving outer environment that surrounds the entire solar system. This region, while seemingly empty, acts as the first layer of interaction between the solar system and the broader galaxy. It filters incoming energetic material in complex ways, depending on particle energy, magnetic orientation, and local density variations. Some particles are deflected back into interstellar space while others penetrate deeper into the heliosphere. The balance between these outcomes depends on energy thresholds and the structure of magnetic fields at the boundary. Over time, this filtering effect influences the overall composition of particles entering the inner solar system. The resulting environment is not static but continuously reshaped by both solar output and galactic motion. This ongoing interaction forms a subtle but persistent layer of energetic variability at the edge of the solar system. Even far from the Sun, traces of this influence remain detectable through particle measurements and radiation signatures. The outer boundary, therefore, represents not a wall but a transition zone where two large-scale environments overlap. This overlap creates a continuous exchange of energy and particles that defines the solar system's first layer of exposure to the galaxy. Within this region, the interaction between charged particles and magnetic fields leads to gradual scattering processes that modify their paths over long distances. These scattering effects are subtle for individual particles, but become important when considering the cumulative flow of matter entering the solar system. The energy distribution of incoming radiation is therefore continuously reshaped by both distance travelled and interactions along the boundary region. Over extended timescales, this leads to a stable but dynamic equilibrium where inflow and outflow remain balanced on average. The region acts as a buffer that moderates the transition between the dense solar environment and the much more diffuse interstellar space. Although no sharp boundary exists, this buffering effect defines the effective outer extent of the solar system's direct influence. Measurements from spacecraft indicate that this region contains a mix of slowed solar wind and incoming interstellar particles interacting in complex patterns. This complex interaction marks the final portion of the outer interstellar boundary, before conditions transition further inward toward planetary space. It establishes the foundational exposure environment that shapes all subsequent regions inside the solar system's stabilizing flux. Beyond the region where interstellar gas and solar influence overlap the outermost gravitational domain of the Sun, extends into a vast cold reservoir of icy bodies known as the Oort cloud. This region is not a compact structure but a diffuse spherical distribution of objects that orbit the Sun at distances so large that the Sun itself appears as only a bright point within a broader galactic backdrop. The material within this region is composed primarily of frozen volatiles, such as water ice, methane ice, and ammonia ice mixed with dust and rocky fragments, that have remained largely unchanged since the earlier stages of solar system formation. These objects are held loosely by the Sun's gravity, and their motions are extremely slow, often taking millions of years to complete a single orbit. In this distant environment, the gravitational influence of the Sun is weak, and external forces begin to play a significant role in shaping orbital behavior, The Oort cloud exists in a delicate balance between solar gravity and external galactic forces. While the Sun provides the central binding force, the gravitational field of the Milky Way exerts a persistent tidal effect across this outer region. This galactic tide does not act as a sudden pull, but as a continuous differential force that gradually shifts the orbits of distant objects. Over long periods of time, this tidal influence can slowly alter the energy of icy bodies, changing their trajectories from stable distant paths into more elongated orbits that bring them closer to the inner solar system. This process occurs gradually, often over timescales that exceed the lifespan of planetary climates or even entire civilizations. In addition to the galactic tide, the Oort cloud is sensitive to the passage of nearby stars. When a star moves through the Sun's galactic neighbourhood, even at distances of several light years, its gravitational field can disturb the loosely bound icy objects at the edge of the solar system. These stellar encounters are rare on human timescales, but over millions of years they accumulate as significant events that reshape the structure of the outer solar system. The effect of such a passing star is not to directly capture or destroy objects, but to subtly alter their velocities, increasing or decreasing orbital energy just enough to destabilize long-term equilibrium. Some objects are pushed outward into even more distant orbits, while others are redirected inward toward the planetary region. The result of these combined influences is a slow but continuous injection of icy bodies into the inner solar system. These objects, once part of a stable distant reservoir, begin long journeys inward as their orbits become elongated and increasingly eccentric. As they approach the warmer regions closer to the Sun, the frozen materials within them begin to respond to solar radiation, leading to gradual sublimation of volatile compounds. This process releases gas and dust, forming extended envelopes that surround the icy cores. These transformations mark the transition of dormant outer solar system material into active cometary bodies. The instability of the Oort cloud is therefore not characterized by sudden collapse or rapid change, but by continuous low-probability perturbations that accumulate over immense time periods. Each object within this region exists in a fragile equilibrium where even the smallest external influence can redirect its path. The cumulative effect of countless weak gravitational interactions creates a dynamic system where motion is always slowly evolving, even though changes may be imperceptible over short intervals. As objects are perturbed inward, they form what are known as long-period comets. These comets enter the inner solar system on highly elongated trajectories, often with orbital periods that span hundreds of thousands or even millions of years. Their appearance in the inner solar system is therefore rare and unpredictable from a human perspective, but statistically continuous over astronomical timescales. Each inbound object carries material that has remained preserved in deep freeze since the formation of the solar system, offering a physical record of early chemical conditions. The journey of these comets inward is influenced by additional gravitational interactions once they begin to approach the planetary region. Encounters with the giant planets, particularly Jupiter and Saturn, can further modify their trajectories, either capturing them into shorter orbits or ejecting them entirely from the solar system. These interactions add another layer of instability, ensuring that the population of long-period comets remains in constant flux. Some are removed permanently from the solar system, while others are redirected into new orbits that may bring them back in future cycles. Within the Oort cloud itself, the distribution of objects is not uniform. Instead, it is shaped by the cumulative history of solar system formation and early dynamical evolution. During the early stages of the solar system, interactions between forming giant planets and smaller icy bodies scattered material outward into distant regions. Over time, this scattering process built the extended reservoir that now defines the Oort cloud. The structure remains loosely bound because it is not a region of formation, but a region of accumulation and retention of scattered remnants. The external galactic environment continues to evolve as the solar system moves through different regions of the Milky Way. Variations in local stellar density and galactic structure alter the frequency and strength of perturbations acting on the Oort cloud. In denser regions of the galaxy, stellar encounters become more frequent, increasing the rate at which comets are destabilized. In more isolated regions, the cloud remains relatively undisturbed, with fewer objects being sent inward. This variation introduces a long-term modulation of cometary influx that is tied to the solar system's galactic orbit. Even without direct stellar encounters, the cumulative effect of galactic tides ensures that the Oort cloud is never completely stable. The continuous stretching and compressing of orbital distributions gradually reshapes the boundary between stable and unstable regions. This slow evolution maintains a steady background level of dynamical activity, even in the absence of discrete external events. Over extremely long timescales, the structure of the Oort cloud itself may shift, reflecting the changing gravitational environment of the galaxy. The objects within this distant reservoir remain largely unaltered physically due to their extreme cold and isolation. Their surfaces preserve chemical signatures from the early solar nebula, making them among the most primitive materials in the solar system. Yet their orbital states are highly sensitive, and it is this combination of physical stability and dynamical fragility that defines the region. The Oort cloud therefore represents a vast quiet source of potential motion, where dormant objects wait for subtle gravitational influences to alter their paths. As the solar system continues its journey through the galaxy, the Oort cloud remains an interface between solar gravity and external galactic forces. It is neither fully stable nor fully active, but exists in a continuous state of slow transformation, driven by weak and distant interactions. These interactions ensure that even the most remote reaches of the solar system contribute over time to the dynamic evolution of its inner regions. Beyond the distant spherical reservoir of icy bodies, the solar system contains a broad flattened region populated by small icy remnants known as the Kuiper belt. This region extends from the orbit of Neptune outward and forms a disk-like structure aligned with the general plane of planetary motion. The material within this belt consists of frozen volatiles mixed with rocky components that never fully accreted into larger planets during the early formation of the solar system. These objects orbit the Sun in relatively stable but slowly evolving paths, shaped primarily by the gravitational influence of the outer planets, especially Neptune. The environment here is sparse, yet far more structured than the distant cloud of objects beyond it, and it reflects a long history of orbital shaping and gravitational sorting. Within the Kuiper belt, orbital dynamics are dominated by resonances created by Neptune's gravitational field. These resonances occur when orbiting bodies complete a fixed ratio of revolutions relative to Neptune, leading to repeated gravitational interactions at regular intervals. Over time, these interactions can stabilize certain orbits, while destabilizing others, creating gaps and clusters in the distribution of objects. Some regions become relatively empty due to long-term clearing, while others contain concentrated populations where orbital resonance provides stability. This structure is not static, but continuously maintained by the ongoing gravitational influence of Neptune, as both it and the belt objects orbit the Sun. The objects within this region remain extremely cold, preserving volatile compounds in solid form. Because solar radiation is weak at these distances, surface temperatures remain low enough for ices to remain stable over billions of years. However, even in this distant environment, subtle processes continue to alter the surfaces of these bodies. Cosmic radiation slowly modifies surface chemistry, breaking molecular bonds and creating thin layers of altered material. Microscopic impacts from dust and small particles gradually reshape surface textures, producing regolith layers that accumulate over long timescales. These processes operate slowly but continuously, ensuring that even seemingly inert objects are subject to gradual change. The Kuiper Belt also serves as a source region for a class of objects known as short-period comets. Unlike long-period comets originating from more distant regions, these bodies have orbits that bring them into the inner solar system on relatively regular timescales. Their paths are often shaped by close gravitational encounters with Neptune and other giant planets, which can redirect them inward. Once perturbed, these objects transition from stable distant orbits into more elliptical trajectories that cross the planetary region. As they move inward, solar heating begins to alter their physical structure, causing sublimation of surface ices and the formation of gaseous envelopes. This transition from stable Kuiper Belt object to active comet represents a key pathway by which material from the outer solar system is redistributed inward. The process is not instantaneous, but occurs through a series of gravitational interactions and orbital adjustments. Each encounter with a massive planet can slightly change the orbit of a small body, gradually increasing orbital eccentricity until the object becomes dynamically unstable in its original region. Over time, this creates a continuous flux of material moving from the outer solar system toward the inner planetary zone. The structure of the Kuiper Belt is not uniform but exhibits regions of varying density and composition. Some areas contain dense clusters of objects while others are relatively sparse. These variations reflect both the initial conditions of solar system formation and the long-term influence of planetary migration. Early in the history of the solar system, the outer planets are believed to have moved slightly from their original positions, redistributing material and reshaping the distribution of small bodies. This migration left behind a complex orbital architecture that continues to influence the present-day structure of the belt. In addition to Neptune's influence, mutual gravitational interactions between Kuiper Belt objects themselves contribute to slow changes in orbital configurations. Although individual objects are small, their collective interactions over long periods can lead to cumulative effects. These interactions are typically weak, but they contribute to the gradual diffusion of orbital elements, slowly altering eccentricities and inclinations. Over very long timescales, this leads to a steady reconfiguration of the belt structure. The Kuiper Belt also contains larger dwarf planets, which have sufficient mass to maintain nearly spherical shapes under their own gravity. These bodies occupy dynamically interesting regions where their gravitational influence can affect nearby smaller objects. Their presence adds complexity to the local environment, introducing additional sources of orbital perturbation. Some of these larger bodies possess thin atmospheres or transient surface activity when they approach slightly warmer regions of their orbits, though most remain frozen and inactive for the majority of their orbital cycles. The outer edge of the Kuiper Belt gradually transitions into more diffuse regions where object density decreases significantly. Beyond this boundary lies the scattered disk, a region populated by objects with highly elongated and inclined orbits. These objects are thought to have been displaced from the Kuiper Belt through gravitational interactions, particularly with Neptune. Their orbits are less stable and more dynamically active, reflecting a history of repeated perturbations. Despite its relative stability compared to more distant regions, the Kuiper Belt is not a static structure. It is continuously shaped by gravitational forces, radiation effects, and collisional processes. Over time, these influences ensure that the population of objects is slowly evolving, even though changes occur over timescales far longer than human observation periods. The region acts as both a remnant of early solar system formation and a dynamic source of material that can be transported inward. The Kuiper belt therefore represents a key transitional zone between the stable inner planetary system and the distant, loosely bound outer reservoirs of icy bodies. It contains both preserved ancient material and dynamically evolving objects that respond to ongoing gravitational interactions. Through these processes, the region contributes to the continuous redistribution of matter throughout the solar system, linking distant cold reservoirs to the warmer inner regions where planetary environments dominate. Beyond the structured band of icy bodies in the Kuiper belt, the outer solar system extends into a more diffuse and dynamically complex region, known as the scattered disk. This region contains objects that were once part of more stable orbits, but have been displaced through repeated gravitational interactions, primarily with Neptune. Unlike the relatively ordered structure of the Kuiper belt, the scattered disk is characterized by highly elongated, inclined, and often unstable trajectories that carry objects far from the planetary plane. These bodies move through vast distances over long orbital periods, creating a region where motion is slow on short timescales, but highly variable over millions of years. The scattered disk exists as a transitional reservoir between the Kuiper belt and the distant Oort cloud. Objects within it experience a wide range of orbital energies, and their paths are continually reshaped by past and occasional future encounters with the giant planets. Neptune plays a central role in this dynamical evolution, acting as both a source of perturbations and a gravitational gatekeeper that can either scatter objects outward or redirect them inward. Over time, repeated interactions accumulate, gradually increasing orbital eccentricity until some objects leave the region entirely. The physical composition of scattered disk objects is similar to that of Kuiper belt bodies, consisting primarily of frozen volatiles mixed with rocky material. However, their more extreme orbital paths expose them to a wider range of solar distances, resulting in varying thermal histories. When these objects approach closer to the Sun, they experience limited surface heating that can trigger partial sublimation of volatile compounds. When they retreat to distant regions, temperatures drop again, allowing ices to resolidify. This cyclical thermal variation leads to slow changes in surface structure over long timescales. Unlike the relatively stable Kuiper belt, the scattered disk is inherently unstable in a statistical sense. Individual objects may remain in the region for hundreds of millions or even billions of years, but their orbits are constantly subject to small perturbations that gradually alter their trajectories. These perturbations arise from gravitational interactions with Neptune, as well as weaker influences from other giant planets and cumulative effects of distant encounters. Over time, these small changes can lead to significant orbital migration. Some scattered disk objects eventually evolve into orbits that intersect the paths of the giant planets. When this occurs, they may experience strong gravitational scattering events that dramatically reshape their trajectories. These encounters can send objects inward toward the inner solar system, or eject them outward into distant, loosely bound or even unbound orbits. This process contributes to a continuous exchange of material between different regions of the solar system, linking distant reservoirs with more central planetary zones. The scattered disk also serves as an important source of short-lived cometary bodies. As objects are perturbed inward, they transition from distant cold environments into regions where solar radiation becomes strong enough to alter their physical state. Surface ices begin to sublimate, forming diffuse atmospheres of gas and dust that expand around the nucleus. These changes mark the transformation of inactive icy bodies into active comets that can be observed from the inner solar system. The orbital distribution within the scattered disk is highly extended, with some objects reaching far beyond the main concentration of the Kuiper belt. These distant trajectories overlap partially with the inner regions of the Oort cloud, creating a gradual blending between structured disk-like motion and more isotropic outer distributions. This overlap suggests a continuity between regions rather than sharp boundaries, with gravitational processes acting across broad spatial scales. The long-term evolution of the scattered disk is governed by a combination of chaotic dynamics and slow diffusion. Chaotic dynamics refers to the sensitivity of orbital paths to small changes in initial conditions, where minor perturbations can lead to large differences in long-term outcomes. Diffusion describes the gradual spreading of orbital elements over time due to repeated weak interactions. Together, these processes ensure that the scattered disk remains in constant but slow transformation. The presence of giant planets is essential to the maintenance of this region. Without their gravitational influence, the scattered disk would gradually lose structure, either collapsing into a more stable belt or dispersing entirely into the outer solar system. Instead, the continued presence of Neptune and the other gas giants sustains a state of dynamic equilibrium where objects are neither fully stable nor fully lost but continually redistributed. Objects in the scattered disk often have high orbital inclinations, meaning their paths are tilted significantly relative to the main planetary plane. This inclination contributes to the three-dimensional complexity of the region, extending its influence above and below the ecliptic plane. These tilted orbits further reduce the likelihood of stable long-term configurations, increasing the probability of future perturbations. Over extremely long timescales, scattered disk objects may migrate into entirely different regions of the solar system. Some are sent inward, becoming short-period comets, while others are ejected into interstellar space, escaping the Sun's gravitational influence entirely. This outward loss contributes to the gradual depletion of the region, though new objects are continually supplied through ongoing perturbations from the Kuiper belt. The scattered disk therefore functions as a dynamic exchange zone, where material is constantly redistributed through gravitational interactions. It bridges the stable outer belt and the distant cloud of loosely bound objects, forming a continuum of orbital behavior shaped by planetary influence. Even though individual motions appear slow and distant, the cumulative effect of countless interactions produces a region that is constantly evolving. In this environment, the solar system reveals one of its most persistent sources of dynamical instability. Objects that once formed in relatively circular stable orbits are gradually reshaped into long eccentric paths that connect distant space with the inner planetary regions. Through this process, the scattered disk acts as both a reservoir and a pathway, ensuring that material continues to circulate through the solar system over immense spans of time. Within the outer gravitational influence of the Sun, but far beyond the orbit of the gas giants, a continuous stream of charged particles flows outward from the solar atmosphere. This flow, known as the solar wind, forms a vast expanding medium that fills interplanetary space with a thin plasma composed primarily of electrons and protons. Although extremely diffuse, this medium extends across the entire solar system and shapes the physical conditions experienced by all objects within it. The solar wind does not remain constant but varies with solar activity changing in density, speed and energy depending on conditions at the Sun's surface. The solar wind originates in the Sun's outer atmosphere, where extremely high temperatures allow particles to escape the Sun's gravitational pull. These particles are accelerated outward by thermal pressure and magnetic processes, forming a continuous outward flow that travels at speeds of hundreds of thousands of kilometers per hour. As this plasma expands into space, it carries with it the solar magnetic field, stretching it into a spiral structure that permeates the entire solar system. This magnetic structure influences the motion of charged particles and contributes to the overall shape of the heliosphere. As the solar wind moves outward, it interacts with all planetary environments it encounters. Each planet embedded in this flow experiences a constant bombardment of charged particles, although the intensity of this exposure varies depending on distance from the Sun and the presence of protective magnetic fields. Planets with strong magnetic fields such as Earth and Jupiter deflect much of this incoming plasma, creating protective magnetospheres that redirect charged particles around their atmospheres. However, even with this protection, some particles still penetrate and contribute to radiation environments in near-planet space. The solar wind also interacts with smaller bodies such as asteroids, comets, and interplanetary dust. On these surfaces, the continuous impact of charged particles gradually alters chemical structures, modifying surface materials over long periods. This process, known as space weathering, darkens and chemically transforms exposed materials, slowly changing their optical and physical properties. Over millions of years, these subtle effects accumulate, reshaping the appearance and composition of surfaces throughout the solar system. The structure of the solar wind is not uniform. It contains regions of varying density and speed, including fast and slow streams that originate from different parts of the Sun's surface. Fast solar wind originates from open magnetic field regions, while slower streams emerge from more complex magnetic structures. When these streams interact, they create regions of compression and rarefaction that propagate through space, forming large-scale structures known as co-rotating interaction regions. These structures influence particle distributions and contribute to the variability of space conditions across the solar system. As the solar wind expands outward, it gradually weakens due to the increasing volume of space it occupies. Despite this weakening, it remains a dominant influence throughout the inner and middle solar system. Even at distances far beyond Earth, the solar wind continues to shape the plasma environment, maintaining a broad bubble of solar influence known as the heliosphere. This bubble represents the region where solar wind pressure balances the pressure of the surrounding interstellar medium. The heliosphere is not a static sphere, but a dynamic, constantly changing structure. Its size and shape vary depending on solar activity and the conditions of the surrounding interstellar environment. At its outer boundary, the solar wind slows down significantly as it encounters the incoming interstellar medium, forming a region of turbulent interaction where plasma conditions become increasingly complex. This boundary marks the transition between solar-controlled space and the broader galactic environment. Within the solar wind, energetic particles can be accelerated to extremely high energies through interactions with shock fronts and magnetic structures. These energetic particles, often referred to as solar energetic particles, can travel rapidly across the solar system, reaching planetary environments and contributing to radiation exposure. Their occurrence is typically associated with periods of intense solar activity, such as solar flares and coronal mass ejections, which release large amounts of energy into the surrounding plasma. The continuous nature of the solar wind means that the entire solar system is immersed in a moving environment of charged particles. This environment is not static but constantly evolving as the Sun rotates and its magnetic field changes configuration. As a result, the conditions experienced at any given location in space can vary over time, even without changes in distance from the Sun. This variability introduces a persistent dynamic element into the solar system's overall structure. The interaction between the solar wind and planetary atmospheres plays an important role in atmospheric evolution. Over long periods, charged particles can contribute to atmospheric escape, particularly for lighter elements at the upper edges of atmospheres. While planetary magnetic fields reduce this effect, they do not eliminate it entirely. In this way, the solar wind acts as a slow but continuous agent of atmospheric modification. At large distances, the solar wind transitions into a region where it begins to mix with interstellar material. This transition region is marked by a gradual slowing of the outward flow and an increase in turbulence. The mixing of solar and interstellar particles creates complex plasma interactions that influence the structure of the outer heliosphere. These processes occur over vast spatial scales and contribute to the overall balance between solar output and galactic environment. Throughout the solar system, the solar wind establishes a background condition of continuous particle flow. It connects the Sun directly to every region of space within its influence, ensuring that no part of the solar system exists in complete isolation. Even the most distant objects within the heliosphere remain embedded within this expanding plasma environment, which carries both energy and magnetic structure across immense distances. Over time, variations in solar wind intensity reflect changes in the Sun's activity cycle. During periods of increased activity, the solar wind becomes more energetic and structured, increasing radiation levels throughout the solar system. During quieter periods, the flow becomes more uniform and less intense. These cycles introduce long-term variability into the space environment, influencing conditions across all planetary systems. The solar wind therefore represents one of the most fundamental forces shaping the solar system's environment. It defines the medium through which all interplanetary interactions occur and establishes the baseline conditions for radiation plasma behavior and magnetic structure throughout space. Within the broad influence of the solar wind, the solar system is continuously exposed to a stream of extremely energetic particles originating from outside the Sun's immediate environment. These particles, known as galactic cosmic rays, are composed primarily of protons and atomic nuclei that have been accelerated to near-light speeds by distant astrophysical events, such as supernova explosions and energetic stellar remnants. As they travel through interstellar space, they carry information about extreme processes occurring far beyond the solar system, yet they arrive here as an invisible and persistent background of high-energy radiation. When galactic cosmic rays enter the solar system, they first encounter the heliosphere, where the outward-moving solar wind and its embedded magnetic field act as a partial barrier. This barrier does not block all incoming particles, but modifies their trajectories, scattering and slowing some, while allowing the most energetic to pass through with little deflection. The effectiveness of this modulation depends on solar activity, with stronger solar wind conditions reducing the intensity of incoming cosmic radiation, and weaker conditions allowing greater penetration. As these high-energy particles move inward, they interact with the solar wind plasma and magnetic structures, producing complex patterns of scattering and energy loss. Some particles are deflected back toward interstellar space, while others continue deeper into the solar system, gradually losing energy through repeated interactions. Despite this filtering effect, a significant fraction of galactic cosmic rays reach the inner solar system, contributing to a constant background of radiation that is present at all planetary distances. When these particles encounter planetary environments, they interact with atmospheres and magnetic fields in ways that produce secondary cascades of particles. In Earth's atmosphere, for example, incoming cosmic rays collide with atmospheric nuclei, generating showers of secondary particles that spread through the upper atmosphere and occasionally reach the surface. These cascades are part of a continuous process that connects distant astrophysical events to local planetary environments through chains of high-energy interactions. The energy of galactic cosmic rays is sufficient to penetrate significant amounts of material, including spacecraft shielding and planetary atmospheres. This penetrating ability makes them a persistent factor in space environments, influencing both physical systems and biological conditions over long timescales. Although the flux of these particles is relatively low compared to solar wind particles, their individual energy levels are extremely high, making each interaction significant at the microscopic scale. Within the heliosphere, the intensity of galactic cosmic rays is not uniform. It varies with solar cycle conditions and the structure of the heliospheric magnetic field. During periods of high solar activity, the increased turbulence and magnetic complexity of the solar wind provides stronger shielding, reducing cosmic ray penetration. During quieter periods, this shielding weakens, allowing a greater number of high-energy particles to reach the inner solar system. This cyclical modulation creates a slowly varying radiation environment that changes over time. As galactic cosmic rays propagate inward, they contribute to the ionization of interplanetary space. When these particles interact with neutral atoms and molecules in sparse regions of space, they strip electrons and produce ions, altering the electrical properties of the medium. This ionization influences the behavior of plasma structures and contributes to the overall electrical balance of the heliosphere. Even though the density of matter in these regions is extremely low, the continuous nature of cosmic ray bombardment ensures that ionization remains an ongoing process. The interaction between galactic cosmic rays and solar system materials also leads to the production of secondary radiation. When high-energy particles collide with solid surfaces, they can produce neutrons, gamma rays, and other secondary particles that propagate outward from the point of impact. Over long periods, this process contributes to subtle changes in the chemical and structural composition of exposed materials, particularly on airless bodies such as the Moon and asteroids. In addition to direct interactions, galactic cosmic rays play a role in shaping the long-term radiation environment of planetary systems. Their continuous flux provides a baseline level of high-energy exposure that persists regardless of solar conditions. This baseline is only slightly modified by solar modulation, making cosmic rays one of the most stable sources of energetic particles within the solar system. Their presence ensures that even in the absence of solar activity, space remains a highly energetic environment. The paths of these particles through the heliosphere are not simple straight lines, but complex trajectories shaped by magnetic fields and turbulence. As they travel inward, they undergo repeated scattering events that alter both their direction and energy. This results in a diffusive propagation pattern where particles spread gradually through space, rather than moving along direct paths. The complexity of this motion makes it difficult to trace individual particles back to their exact sources in the galaxy. Despite this complexity, measurements of cosmic ray composition reveal important information about their origins. The relative abundance of different atomic nuclei within the cosmic ray population reflects processes occurring in distant astrophysical environments. These measurements indicate that cosmic rays originate from a wide range of energetic events, distributed throughout the galaxy rather than a single source. Each particle therefore represents a small sample of distant cosmic conditions. As galactic cosmic rays continue to move through the solar system, they form an invisible but persistent energetic background that permeates all regions from the outer heliosphere to near planetary surfaces. Their presence links the solar system to the broader galaxy in a continuous exchange of high-energy matter and radiation. This connection ensures that the solar system is never fully isolated from external astrophysical activity. Over long timescales, variations in cosmic ray intensity may influence the overall radiation environment experienced by planetary systems. These variations are tied to both solar activity and the solar system's movement through different regions of the galaxy. As the heliosphere changes shape and strength, the degree of shielding against incoming cosmic radiation also changes, leading to gradual shifts in the energetic conditions throughout the solar system. Galactic cosmic rays therefore represent one of the most pervasive and energetic influences within the solar system. They originate far beyond the Sun, traverse vast interstellar distances, and penetrate deep into planetary environments, carrying with them the imprint of distant cosmic events, while continuously shaping the radiation landscape of the entire system. Within the inner structure of the solar system, a broad region of small rocky and metallic bodies forms a dispersed ring known as the asteroid belt. This region lies between the orbits of Mars and Jupiter, and contains a vast number of objects that range in size from fine dust to dwarf planet-scale bodies. These objects are remnants of early solar system formation material that never fully accreted into a single planet due to the strong gravitational influence of Jupiter. The asteroid belt is not densely packed, but it is dynamically active with constant subtle interactions, shaping the long-term evolution of orbital paths. The gravitational field of Jupiter plays the central role in structuring this region. Its immense mass creates orbital resonances that influence the motion of asteroids over long periods. When an asteroid's orbital period matches a simple ratio with Jupiter's period, repeated gravitational tugs accumulate over time, gradually altering its orbit. Some resonances create gaps in the belt, where objects are cleared out, while others stabilize specific regions where asteroids can persist. These resonance structures define much of the belt's internal architecture and create a complex pattern of stability and instability. Although individual asteroids or widely spaced collisions still occur over astronomical timescales, when impacts happen, they break larger bodies into smaller fragments, contributing to a continuous process of fragmentation and redistribution. Over millions of years, this collisional evolution produces families of asteroids that share similar orbital characteristics, suggesting a common origin from past breakup events. The resulting debris ranges from large irregular fragments to fine dust that slowly spreads throughout the inner solar system. The physical composition of asteroid belt objects varies depending on their location within the region. Some are rich in metallic elements such as iron and nickel, while others contain more silicate rock or carbon-rich material. This variation reflects differences in temperature during early solar system formation, when material closer to the Sun was heated and partially differentiated, while more distant regions retained volatile, rich compositions. The asteroid belt therefore preserves a record of thermal gradients that existed during the early stages of planetary formation. The belt is not static, but slowly evolving under the combined influence of gravitational perturbations and collisional processes. Over long timescales, these effects cause gradual changes in orbital distributions, with some objects being nudged into new trajectories. A fraction of asteroids are displaced inward toward the inner solar system, while others are pushed outward or ejected entirely. This slow redistribution contributes to the ongoing exchange of material between different regions of the solar system. One important outcome of this dynamical activity is the production of near-Earth objects. These are asteroids whose orbits bring them into the inner solar system, sometimes crossing the path of Earth. Their origin can often be traced back to specific resonant regions within the asteroid belt, where gravitational interactions with Jupiter gradually increase orbital eccentricity. Over time, these objects transition from stable belt orbits into dynamically unstable paths that bring them closer to the Sun. Despite its vast number of objects, the asteroid belt contains very little total mass compared to a planet. The combined mass of all asteroids is far less than that of Earth's moon, indicating that the region represents material that never fully coalesced into a planetary body. Jupiter's early influence is believed to have prevented this accumulation, by stirring the region and increasing collision velocities, making accretion inefficient and destructive rather than constructive. The surfaces of asteroids are continuously modified by exposure to the space environment. Without atmospheres or magnetic fields, these bodies are directly exposed to solar radiation, cosmic rays, and micrometeoroid impacts. Over time, these processes alter surface chemistry and structure, producing layers of weathered material that differ from their interiors. This space weathering darkens surfaces and gradually changes their spectral properties, making them less reflective and more uniform in appearance. Some asteroids show evidence of past thermal or structural evolution, including differentiation into layered interiors. These bodies may have once been large enough to partially melt, allowing heavier materials to sink toward their centers, while lighter materials rose to the surface. Subsequent collisions then disrupted these early structures, fragmenting them into smaller bodies that now populate the belt. As a result, the asteroid population includes both primitive remnants and fragments of once more complex bodies. The gravitational influence of Mars also plays a secondary role in shaping the inner edge of the asteroid belt. While weaker than Jupiter's influence, Mars can still perturb nearby objects over long periods, contributing to the gradual leakage of material into the inner solar system. This process helps feed the population of near-Earth asteroids and maintains a continuous but low-level flux of material crossing planetary orbits. Within the asteroid belt, there are also regions of relative emptiness known as Kirkwood gaps. These gaps correspond to orbital resonances with Jupiter, where long-term stability is not possible. Objects entering these regions experience repeated gravitational disturbances that eventually alter their orbits, removing them from the resonance zone. The presence of these gaps demonstrates the long-term dynamical sculpting of the belt by planetary gravity. The asteroid belt therefore represents a region where stability and instability coexist over immense timescales. While many objects remain in relatively stable orbits for billions of years, others are continuously shifted through slow, gravitational interactions and collisions. This balance creates a constantly evolving environment where material is redistributed throughout the inner solar system. Over time, the asteroid belt acts as both a reservoir and a source of material for planetary surfaces. Impacts from asteroids have played a significant role in shaping planetary geology, delivering both energy and material to planets over the history of the solar system. Even in the present epoch, this process continues at a reduced but persistent rate. The asteroid belt thus functions as a dynamic intermediate zone linking the outer icy reservoirs of the solar system with the rocky inner planets. Through gravitational interactions, collisions, and slow orbital evolution, it maintains a continuous flow of material across different regions, ensuring that the solar system remains interconnected through both physical and dynamical processes. Within the inner solar system, the region surrounding Jupiter contains one of the most intense and structured radiation environments in the entire planetary system. Jupiter's immense mass generates a powerful magnetic field that extends far into space, forming a vast magnetosphere that dominates the local plasma environment. This magnetic field traps charged particles and organizes them into complex radiation belts that encircle the planet. These belts contain high-energy electrons and ions that move along magnetic field lines, creating a persistent and highly energetic region of space, influenced by both solar wind input and internal plasma sources. The origin of this radiation environment begins with both external and internal contributions. Particles from the solar wind enter the magnetosphere and become trapped by Jupiter's magnetic field, while additional material is supplied by volcanic activity on the moon Io. Io releases large amounts of sulfur and oxygen compounds into space, which become ionized and incorporated into the surrounding plasma environment. These ions are then accelerated by Jupiter's rotating magnetic field gaining energy as they move through the magnetosphere. The combination of these sources creates a dense and dynamic radiation system that is continuously replenished. Within this environment, charged particles follow spiral paths along magnetic field lines, repeatedly bouncing between magnetic poles while slowly drifting around the planet. This motion creates structured radiation belts that vary in intensity depending on altitude and magnetic latitude. The energy levels of particles in these belts can become extremely high, producing conditions that are hostile to spacecraft electronics and sensitive instruments. Even short exposure to this region requires careful shielding and trajectory planning to avoid damage from accumulated radiation. The structure of Jupiter's magnetosphere is not static, but changes in response to variations in solar wind pressure and internal plasma dynamics. When the solar wind strengthens, the magnetosphere is compressed, altering the distribution of trapped particles. When it weakens, the magnetosphere expands outward, allowing the radiation belts to spread over a larger region of space. These fluctuations introduce variability into the radiation environment, even though the overall structure remains stable over long periods. Beyond the main radiation belts, Jupiter's magnetosphere also contains regions of lower particle density, where magnetic field lines extend far into space before reconnecting. These regions allow for the exchange of particles between the magnetosphere and surrounding space, contributing to a continuous flow of material. Some particles escape entirely while others are recaptured and re-energized within the magnetic field system. This exchange creates a dynamic equilibrium between confinement and loss. The radiation environment near Jupiter extends far beyond the planet itself, influencing nearby moons and spacecraft trajectories. Moons such as Europa Ganymede and Callisto are embedded within this energetic environment and experience continuous exposure to high-energy particles. Their surfaces are gradually modified by this radiation, leading to chemical changes in surface ice and the production of altered compounds. Over long timescales, these processes contribute to the evolution of surface properties and subsurface chemistry. Among these moons, Ganymede is unique because it possesses its own intrinsic magnetic field. This smaller magnetosphere interacts with Jupiter's larger field, creating complex patterns of magnetic reconnection and particle flow. The interaction between the two magnetic systems produces localized regions where particles are redirected and accelerated in ways that differ from the surrounding environment. This makes the space around Ganymede dynamically distinct within the broader Jovian system. The energy of particles trapped in Jupiter's magnetosphere is sufficient to produce secondary radiation when they collide with matter. These interactions generate X-rays and other high-energy emissions that can be detected remotely, providing insight into the structure and behavior of the radiation belts. The continuous production of such emissions indicates that the system is constantly active and evolving, even in the absence of external disturbances. The spatial extent of Jupiter's magnetosphere is so large that it can be considered a dominant structure within the inner solar system. It stretches millions of kilometers into space, interacting with the solar wind and shaping the flow of plasma in its vicinity. At the boundary where solar wind pressure balances magnetic pressure, complex shock structures form, marking the transition between planetary influence and interplanetary space. Within this system, the movement of particles is governed by electromagnetic forces rather than simple gravitational motion. Charged particles respond to magnetic fields in complex ways, following curved trajectories that depend on both their energy and the structure of the field. This leads to a highly organized yet continuously changing system, where particle motion is constrained but not static. The presence of such an intense radiation environment makes Jupiter one of the most extreme natural particle accelerators in the solar system. Energy is transferred from the planet's rotation into charged particles, effectively converting rotational energy into radiation. This process sustains the radiation belts over long periods and ensures that the environment remains energetically active. Despite its intensity, this radiation system is part of a broader balance within the solar system's inner regions. It represents one of several mechanisms by which energy and particles are redistributed across space. The interactions between solar wind planetary magnetic fields and internal plasma sources create a complex network of energetic exchange that extends across multiple scales. The Jovian radiation environment therefore stands as a key example of how planetary magnetic fields can transform space into a structured energetic system. It demonstrates that even in regions far from the Sun's immediate influence, local planetary conditions can generate extreme and persistent radiation hazards that shape the surrounding space environment. Within the inner solar system, a thin but constantly active layer of particulate matter extends along the orbital paths of planets. This layer, composed of microscopic dust grains and small fragments of rock, forms a diffuse environment known as the interplanetary dust medium. These particles originate from a combination of asteroid collisions, cometary activity, and long-term erosion of small bodies exposed to solar radiation and micrometeoroid impacts. Although each individual particle is extremely small, their combined presence creates a widespread and persistent material background throughout planetary space. The motion of interplanetary dust is influenced by several subtle forces that act continuously over time. Solar radiation exerts a gentle pressure on these particles, gradually altering their orbits and causing slow inward spiraling toward the Sun. This process, known as Poynting-Robertson drag, results from the interaction between sunlight and moving particles, where absorbed and re-emitted radiation leads to a loss of orbital energy. Over long timescales, this mechanism causes dust to migrate inward, continuously replenishing material in the inner solar system while depleting outer regions. Electromagnetic forces also play a role in shaping dust behavior. As particles become electrically charged through exposure to solar ultraviolet radiation and plasma interactions, they begin to respond to the solar wind's magnetic field. This introduces additional complexity into their motion, particularly for the smallest grains, which can be significantly deflected or accelerated depending on local plasma conditions. The combined influence of radiation pressure and electromagnetic interaction produces highly varied and evolving orbital patterns. Collisions between dust particles, though rare on short timescales, contribute to the gradual fragmentation and redistribution of material. When collisions occur, they can break larger grains into smaller fragments, increasing the overall number of particles while reducing average size. Over millions of years, this collisional evolution helps maintain a steady population of fine dust distributed throughout the inner solar system. The resulting environment is a dynamic balance between creation, destruction, and transport. This interplanetary dust forms faint structures known as dust bands and zodiacal clouds, which extend along the plane of planetary orbits. These structures are not sharply defined but appear as broad, diffuse concentrations of scattering material illuminated by sunlight. The brightness of these regions is extremely low, yet they represent a continuous presence of particulate matter filling the space between planets. Their structure reflects the combined contributions of multiple source regions, including the asteroid belt and active cometary pathways. Cometary activity plays a particularly important role in supplying fresh dust to the inner solar system. As comets approach, the Sun's solar heating causes volatile materials to sublimate, releasing gas and entrained dust into surrounding space. This material forms extended tails that spread along the comet's orbit, gradually dispersing into the interplanetary medium. Over time, these dust streams become detached from their parent comets, contributing to long-lived background populations of fine particles. The distribution of interplanetary dust is not uniform but varies with distance from the Sun and proximity to source regions. Higher concentrations are found near the asteroid belt and along cometary orbital paths, while more diffuse conditions exist farther away. These variations reflect the ongoing balance between dust production, transport, and removal processes that operate throughout the solar system. Despite its low density, interplanetary dust plays an important role in the energy balance of the solar system. These particles scatter and absorb sunlight, contributing to faint optical phenomena such as the zodiacal light, a subtle glow visible in dark skies near the Sun's position. This glow represents sunlight reflected from countless individual grains, distributed across vast volumes of space. Dust particles also interact with planetary atmospheres when they enter through atmospheric drag. As they descend, they typically burn up due to frictional heating, producing meteors. This process introduces extraterrestrial material into planetary environments, delivering trace elements and contributing to atmospheric chemistry. On Earth, this continuous influx of dust represents a steady exchange of material between space and atmosphere. Over long periods, the interplanetary dust environment evolves under the combined influence of source replenishment and removal processes. While collisions and cometary activity generate new particles, radiation forces and solar-wind interactions remove or redistribute them. This balance ensures that the dust population remains relatively stable on large scales, even as individual particles follow complex and changing trajectories. The presence of this dust also affects spacecraft operating within the inner solar system. Even microscopic impacts at high relative speeds can cause gradual erosion of exposed surfaces. Although each impact is small, the cumulative effect over time contributes to surface wear and material degradation. This makes interplanetary dust a subtle but persistent environmental factor in space exploration. The dust medium therefore acts as a connecting layer between larger bodies and the surrounding space environment. It carries material from asteroids and comets into broader circulation, redistributing it across planetary regions. Through this process, it links the solid components of the solar system with the dynamic plasma and radiation environments described in surrounding regions. Over astronomical timescales, the continuous cycling of dust ensures that the inner solar system remains embedded in a constantly renewed particulate environment. This environment is shaped by both creation and destruction, driven by the ongoing activity of small bodies and the persistent influence of solar forces. It represents one of the most widespread yet least visible components of the solar system's structure. The interplanetary dust medium therefore forms a quiet but essential layer of material that permeates the space between planets. It connects distant sources of debris to local planetary environments, maintaining a continuous flow of microscopic matter throughout the inner solar system. Within the inner solar system, the space environment becomes increasingly shaped by sudden and localized releases of energy from the Sun's surface. These releases, known as solar flares, originate in regions of intense magnetic complexity, where magnetic field lines become twisted, stressed, and eventually reconfigured. When this reconfiguration occurs, large amounts of stored magnetic energy are rapidly converted into heat radiation and particle acceleration. The result is a sudden increase in high-energy emissions that propagate outward through space at the speed of light. Solar flares are not uniform events but vary widely in magnitude and structure. Some are relatively small and localized, while others involve vast regions of the solar atmosphere and release energy equivalent to billions of nuclear detonations combined. Regardless of scale, each flare represents a rapid restructuring of magnetic fields in the solar atmosphere. This restructuring occurs in the corona, the Sun's outermost atmospheric layer where temperatures are extremely high and plasma is fully ionized. The energy released during a solar flare is distributed across multiple forms. Electromagnetic radiation spans a wide range of wavelengths, including X-rays and ultraviolet light, which travel outward and can reach planetary environments within minutes. At the same time, energetic particles are accelerated along magnetic field lines, forming beams of high-speed protons and electrons that move through interplanetary space. These particles can take longer to arrive but carry significant energy capable of altering space conditions far from the Sun. When these energetic emissions travel outward, they interact with the solar wind, modifying its density and structure. The sudden injection of energy can create shock fronts that propagate through the heliosphere, disturbing the surrounding plasma environment. These disturbances are not localized but expand across large regions of space, affecting planetary magnetospheres and altering radiation conditions throughout the inner solar system. At Earth's distance, solar flares are observed as sudden increases in high-energy radiation that can affect the upper atmosphere. The ionosphere, a region of charged particles surrounding the planet, responds quickly to incoming X-rays and ultraviolet radiation. Increased ionization in this region can temporarily change its electrical properties, affecting how radio waves propagate through the atmosphere. These changes occur rapidly, but typically dissipate as the flare subsides. The accelerated particles associated with solar flares can also interact directly with planetary magnetic fields. When they encounter these fields, they spiral along magnetic field lines and become trapped in radiation belts or redirected toward polar regions. This process leads to localized increases in particle precipitation, where energetic particles enter the upper atmosphere and deposit energy through collisions with atmospheric molecules. Solar flares are closely linked to coronal mass ejections, although the two phenomena are not identical. A coronal mass ejection involves the release of large amounts of solar plasma into space, forming a massive cloud of charged particles that travels outward over hours or days. When these ejections occur alongside flares, their combined effects can significantly enhance space weather disturbances, increasing both radiation levels and magnetic field variability across planetary environments. The propagation of flare-driven disturbances through the solar system depends on the structure of the solar wind. Fast-moving streams can carry shock fronts more efficiently, while slower regions may cause interactions that modify the shape and intensity of the disturbance. As these structures travel outward, they gradually expand and weaken, but they can still influence space conditions at great distances from the Sun. Within the heliosphere, these energetic events contribute to a constantly changing radiation environment. Even in periods of relative solar calm, smaller flares occur regularly, ensuring that the solar system is never completely free from episodic energy releases. Over longer timescales, these repeated events form a pattern of variability that shapes the background conditions of interplanetary space. The effects of solar flares are not limited to immediate radiation impacts. Over extended periods, repeated energetic events can influence atmospheric evolution on planets by driving gradual loss of atmospheric particles. In upper atmospheric layers, energetic radiation can impart enough energy to some particles to overcome gravitational binding, allowing them to escape into space. While this process is slow, it contributes to long-term atmospheric change. The frequency of solar flares follows a cycle related to the Sun's magnetic activity cycle. During periods of high activity, flares occur more frequently and with greater intensity, while quieter periods exhibit reduced flare production. This cyclical behavior introduces long-term variability into the energetic environment of the solar system, affecting radiation exposure levels across all planetary orbits. The solar atmosphere where flares originate is a highly structured environment dominated by magnetic loops and plasma flows. These structures store energy over time as magnetic fields become increasingly complex. When stability is lost, the system rapidly reorganizes, releasing stored energy in a sudden and powerful event. This process reflects the continuous interaction between plasma motion and magnetic field evolution. As flare emissions propagate outward, they become part of the broader heliospheric environment, contributing to the overall variability of space conditions. Their influence extends beyond immediate radiation bursts, shaping particle distributions and plasma dynamics across vast regions. Even after the initial event has passed, residual effects continue to propagate through the solar wind. Solar flares therefore represent one of the most dynamic and energetic processes within the solar system. They link the Sun's internal magnetic activity directly to conditions throughout interplanetary space, ensuring that changes at the solar surface are rapidly transmitted across the entire heliosphere. Within the inner solar system, large-scale expulsions of solar plasma emerge as structured clouds of charged material known as coronal mass ejections. These events originate in the Sun's corona, where magnetic fields store vast amounts of energy through twisting and shearing motions of hot plasma. When these magnetic structures become unstable, they release energy by ejecting massive quantities of solar material into space. This material consists primarily of protons, electrons, and embedded magnetic fields carried outward as a coherent expanding structure. A coronal mass ejection does not occur as a simple burst, but as a layered release of plasma that evolves as it moves away from the Sun. The leading edge often forms a shock front, compressing and heating the surrounding solar wind. Behind this front lies a dense magnetic structure that maintains coherence over large distances. As the ejection travels outward, it expands and interacts with the background solar wind, gradually changing shape and intensity, while still preserving its overall structure. The speed of these ejections varies widely. Some move relatively slowly, taking several days to reach planetary distances, while others travel at extremely high speeds, reaching Earth's orbit in less than a day. The variation depends on the amount of energy released during the magnetic restructuring process in the corona. Faster events tend to produce stronger shocks and more intense disturbances in interplanetary space. As coronal mass ejections propagate through the heliosphere, they modify the local plasma environment. The compressed leading edge increases particle density and magnetic field strength, creating regions of enhanced pressure within the solar wind. These regions interact with the ambient plasma, generating turbulence and waves that propagate outward. The resulting disturbance can extend across vast regions of space, affecting planetary environments throughout the inner solar system. When these structures encounter planetary magnetospheres, they can cause significant compression of the magnetic field boundaries. This compression alters the shape and size of magnetospheres, allowing energetic particles to penetrate more deeply into near-planet space. The interaction between ejected solar material and planetary magnetic fields produces complex patterns of energy transfer that vary depending on the strength and orientation of the incoming magnetic structure. At Earth's distance, the arrival of a coronal mass ejection is often associated with increased auroral activity. As charged particles interact with the upper atmosphere, they follow magnetic field lines toward polar regions where they collide with atmospheric gases. These collisions produce light emissions that reflect the transfer of energy from solar particles to atmospheric molecules. Although visually striking in observation, these processes represent the continuous interaction between solar output and planetary magnetic protection systems. Coronal mass ejections also contribute to long-term changes in space weather conditions. When multiple events occur in succession, they can create overlapping disturbances in the solar wind, leading to extended periods of heightened particle flux and magnetic variability. These conditions persist until the plasma structures gradually dissipate and merge into the background solar wind. The interaction between ejections and the heliosphere is influenced by the structure of the interplanetary magnetic field. As the ejected plasma carries its own magnetic configuration outward, it can reconnect with the surrounding field lines. Magnetic reconnection is a process where magnetic field lines break and reform, releasing additional energy and altering particle trajectories. This process adds further complexity to the evolution of coronal mass ejections as they travel through space. The outer regions of these ejections eventually disperse as they lose coherence, blending into the broader solar wind environment. Despite this dissipation, the energy and particles they inject into the heliosphere continue to influence space conditions long after the initial event. This lingering effect contributes to the overall variability of the solar system's plasma environment. Coronal mass ejections are closely linked to the solar magnetic cycle, which governs the long-term behavior of solar activity. During periods of increased magnetic complexity, such events occur more frequently and with greater intensity. During quieter phases, they become less common and generally weaker. This cyclical variation ensures that the heliosphere experiences alternating periods of relative stability and increased dynamical activity. As these ejections move through space, they interact with other structures in the solar wind, including high-speed streams originating from coronal holes. When these different plasma flows intersect, they create regions of enhanced turbulence and compression. These interactions further shape the distribution of energy and particles throughout the heliosphere. The influence of coronal mass ejections extends beyond immediate space weather effects. Over long timescales, repeated exposure to these events can contribute to gradual atmospheric loss on planets without strong magnetic shielding. Energetic particles associated with these events can transfer enough energy to atmospheric particles to allow some of them to escape into space, slowly altering atmospheric composition. The heliosphere acts as a dynamic system where coronal mass ejections represent one of the most significant drivers of short-term variability. They introduce sudden changes in density, magnetic structure, and energy distribution across vast regions of space. Even though each event is temporary, the cumulative effect of many such events defines the evolving character of the solar system's plasma environment. Within this environment, the propagation of ejected material is shaped by both internal solar conditions and external interstellar pressure. As the heliosphere expands and contracts in response to these factors, the behavior of coronal mass ejections also changes. Their expansion rates, interaction strength, and spatial influence are all affected by the surrounding balance of forces at the edge of solar influence. Coronal mass ejections therefore represent a central mechanism by which the Sun continuously reshapes the space environment of the entire solar system. They connect deep solar magnetic processes to distant planetary regions, transmitting energy and matter across vast distances and maintaining a state of ongoing dynamic interaction throughout interplanetary space. Within the inner solar system, the region surrounding Earth exists as a complex interface between solar radiation, planetary magnetic shielding, and a continuously changing population of artificial objects. This region is known as near-Earth space, and it contains a dense mixture of natural plasma-charged particles and human-made satellites that all occupy overlapping orbital paths. The environment here is not empty, but structured by gravity, magnetism, and atmospheric boundary effects that create a layered and dynamic system. Earth's magnetic field plays a central role in shaping this environment. Generated by the motion of molten metal in the planet's outer core, the magnetic field extends far into space and forms a protective cavity known as the magnetosphere. This structure deflects much of the incoming solar wind, guiding charged particles around the planet and preventing direct atmospheric erosion. However, the magnetosphere is not a rigid barrier. It constantly responds to changes in solar activity, expanding and contracting as external conditions vary. Within the magnetosphere, charged particles become trapped in regions known as radiation belts. These belts contain high-energy electrons and protons that move along magnetic field lines in spiral trajectories. Their motion is controlled by the balance between magnetic forces and particle energy, producing structured zones of enhanced radiation. These regions vary in intensity depending on solar conditions, with higher activity leading to increased particle injection and acceleration. The interaction between solar wind and Earth's magnetic field produces complex boundary regions where energy is continuously transferred. At the outer edge of the magnetosphere, incoming solar plasma is slowed and deflected, forming a shock-like structure known as the bow shock. Beyond this boundary lies a turbulent region where solar wind particles are redirected around the magnetosphere. Within this region, energy is redistributed through waves and instabilities that propagate through the plasma. Near Earth, the atmosphere itself acts as an additional layer of protection. The upper atmosphere absorbs much of the incoming high-energy radiation, converting it into heat and ionization. This process creates the ionosphere, a region of partially ionized gas that responds strongly to changes in solar radiation. Variations in this region affect the propagation of radio signals and the behavior of charged particles entering the atmosphere. The presence of energetic particles in near-Earth space is not constant, but fluctuates in response to solar activity. During periods of increased solar output, particle flux increases, leading to stronger radiation environments in orbit. During quieter periods, the environment becomes more stable, though a background level of cosmic radiation remains present at all times. This variability creates a constantly changing energetic landscape for all objects in orbit. Artificial satellites operate within this environment, moving through regions of varying radiation intensity and plasma density. These objects are exposed to charged particle bombardment, which can gradually degrade materials and affect electronic systems. Over long durations, this exposure contributes to the slow accumulation of damage in spacecraft components. Despite this, satellites remain operational due to shielding and system design that account for these environmental conditions. In addition to radiation, near-Earth space contains a growing population of orbital debris. This debris consists of defunct satellites, spent rocket stages, and fragments produced by past collisions and disintegration events. These objects move at extremely high velocities relative to one another, making even small particles capable of causing significant impact damage. The distribution of this debris is uneven, with concentrated regions forming in commonly used orbital altitudes. Collisions between debris objects can produce additional fragments, increasing the total number of particles in orbit. This process, known as collisional cascading, has the potential to gradually increase the density of debris in certain regions over time. Even without new launches, the existing population of fragments can evolve dynamically through repeated interactions. The motion of objects in near-Earth space is governed primarily by gravity, but small non-gravitational forces also play a role. Atmospheric drag affects objects in low orbit, gradually reducing their altitude and eventually causing re-entry into the atmosphere. Solar radiation pressure can also influence the orbits of small or lightweight objects, introducing slow changes in their trajectories. The interaction between natural space environment and artificial structures creates a hybrid system where human activity and planetary physics overlap. Satellites measure solar wind conditions, radiation levels, and magnetic field variations, contributing to continuous monitoring of space weather. This data reflects the ongoing interaction between solar activity and Earth's protective systems. Energetic events originating from the Sun, such as flares and coronal mass ejections, propagate through this region and produce rapid changes in environmental conditions. When these disturbances reach Earth, they compress the magnetosphere and increase particle injection into radiation belts. These effects can persist for hours or days depending on the strength of the solar event and the structure of the incoming plasma. Despite these disturbances, the overall structure of near-Earth space remains stable over long timescales. The balance between incoming solar energy, magnetic shielding, and atmospheric absorption maintains a dynamic equilibrium. This equilibrium is constantly adjusted but never fully disrupted, allowing the region to support both natural processes and artificial activity. Near-Earth space therefore represents one of the most complex regions of the solar system. It contains interacting layers of plasma radiation, magnetic fields, and human-made objects, all governed by the continuous influence of solar activity. These combined factors create an environment that is both stable in structure and highly variable in detail, reflecting the constant exchange of energy between the Sun and the Earth system. Closer to the Sun, the environment becomes increasingly dominated by intense radiation and rapidly changing plasma conditions within the solar corona. The corona is the Sun's outermost atmospheric layer, extending far beyond the visible surface and forming a vast region of extremely hot, highly ionized gas. Temperatures in this region reach millions of degrees, far exceeding those of the visible surface below. This counterintuitive heating arises from complex magnetic processes that transfer energy from the Sun's interior into its outer atmosphere. The structure of the corona is shaped by the Sun's magnetic field, which forms loops, arches, and open field lines that extend into space. These magnetic structures are continuously reshaped by the motion of plasma on the solar surface. As charged particles move along magnetic field lines, they carry energy and stress through the coronal environment, gradually building up regions of instability. When these instabilities are released, they contribute to the dynamic behavior observed throughout the solar atmosphere. Within the corona, plasma is not uniformly distributed but arranged in structured regions of varying density and temperature. Some areas are relatively quiet, with smoother magnetic configurations and lower levels of activity. Other regions are highly active, containing tangled magnetic fields and rapidly changing plasma flows. These active regions are the primary sources of energetic events, such as solar flares and coronal mass ejections, which influence the entire solar system. The corona is also the origin point of the solar wind. Here particles gain enough energy to overcome the Sun's gravitational pull and escape into interplanetary space. The exact mechanism by which this acceleration occurs involves a combination of thermal expansion, wave heating, and magnetic reconnection processes. Together, these mechanisms allow plasma to transition from a gravitationally bound state to a continuously flowing outward stream. Magnetic reconnection plays a particularly important role in coronal dynamics. When magnetic field lines become twisted and oppositely directed, they can break and reconnect in new configurations. This process releases large amounts of energy, accelerating particles and heating surrounding plasma. The energy released during reconnection events contributes directly to the heating of the corona and the acceleration of solar wind particles. The corona is not a static layer, but a constantly evolving environment shaped by the rotation of the Sun and the emergence of new magnetic structures from below the surface. As the Sun rotates, different regions of magnetic activity move into and out of view, creating a continuously changing pattern of coronal features. This rotation distributes energetic processes across the solar surface, ensuring that no single region remains dominant for long periods. Coronal holes are regions where magnetic field lines open outward into space, rather than looping back to the surface. These regions allow high-speed solar wind to escape more easily, producing fast-moving streams of charged particles. When these streams interact with slower-moving solar wind, they create large-scale interaction regions that propagate through the heliosphere. These structures contribute to the variability of space conditions throughout the solar system. The density of matter in the corona is extremely low compared to planetary atmospheres, yet its influence extends across vast distances. Because the particles are highly energetic and move at high speeds, even sparse material can carry significant amounts of energy outward into space. This combination of low density and high energy defines the unique character of the coronal environment. The corona also emits radiation across a wide range of wavelengths, including ultraviolet and X-ray emissions. These emissions are produced by high-energy interactions between particles in the hot plasma. Observations of this radiation provide insight into the structure and behavior of the solar atmosphere, revealing the distribution of temperature and magnetic activity across different regions. As coronal material expands outward, it transitions into the solar wind, forming a continuous flow that fills the solar system. This transition is gradual rather than abrupt, with plasma conditions changing continuously as distance from the Sun increases. The boundary between the corona and the solar wind is therefore defined by changing physical conditions rather than a fixed surface. The corona is also the region where the most energetic particles in the solar system are produced. During periods of intense activity, particles can be accelerated to extremely high energies and ejected into space as solar energetic particle events. These particles travel rapidly through the heliosphere and can reach planetary environments within short timescales, contributing to radiation exposure throughout the system. The interaction between coronal plasma and magnetic fields creates a highly structured environment where energy is constantly being stored, released, and redistributed. This dynamic system operates across multiple scales, from small localized loops to large-scale, global magnetic configurations that span the entire solar surface. Each scale contributes to the overall behavior of the corona and its influence on interplanetary space. Despite its extreme conditions, the corona is a key region that connects the Sun's interior processes to the broader solar system environment. It serves as the launching point for the solar wind and the origin of many energetic events that propagate outward through space. Through these processes, the corona plays a central role in shaping the energetic and magnetic structure of the entire solar system. As the outermost solar atmosphere, the corona represents the final stage of solar influence before material enters interplanetary space. From this region, plasma radiation and magnetic structures extend outward, carrying the imprint of solar activity into the heliosphere and beyond. Within the inner solar system, the environment closest to the Sun becomes a domain where extreme radiation, intense gravity, and rapidly shifting thermal conditions dominate all physical processes. This region is defined by the proximity to the solar surface, where energy is emitted in vast quantities, and space is filled with highly energized plasma. Temperatures rise sharply as distance decreases, and material behavior becomes governed by ionization, magnetic confinement, and continuous exposure to intense electromagnetic radiation. Near the Sun, the concept of solid structure begins to break down for most materials. At such high energy levels, atoms exist primarily in ionized states, with electrons separated from nuclei and moving freely within the plasma environment. This creates a medium where electrical and magnetic forces dominate over chemical bonding, and matter behaves as a fluid of charged particles rather than discrete atoms. The result is a dynamic environment where structure is defined by fields rather than fixed physical forms. The gravitational influence of the Sun in this region is extremely strong, shaping the motion of all surrounding material. Objects that approach too closely are subjected to intense tidal forces, which can stretch and deform them depending on their composition and structural strength. Even relatively large bodies are unable to maintain stable long-term structures when exposed to both extreme heat and strong gravitational gradients. Radiation intensity increases dramatically in this inner region. The Sun emits energy across the entire electromagnetic spectrum, including visible light ultraviolet radiation and high-energy X-rays. As distance decreases, the intensity of this radiation increases, rapidly heating surrounding plasma and influencing particle behavior. This energy input drives continuous ionization and maintains the extreme temperature of the surrounding environment. Magnetic fields in this region are highly complex and dynamic. They are generated by the movement of conductive plasma within the Sun and extend outward into surrounding space. These fields interact with charged particles, guiding their motion and shaping large-scale plasma structures. Magnetic loops and arches continuously form and dissolve, reflecting the ongoing motion of plasma beneath the solar surface. Within this environment, particle acceleration processes occur continuously. Charged particles gain energy through interactions with magnetic fields and shock fronts, reaching velocities that allow them to escape the Sun's gravitational influence. These accelerated particles contribute to the solar wind and form the foundation of energetic particle populations that propagate throughout the solar system. The region close to the Sun also contains areas of intense turbulence. Plasma flows are highly variable, with rapid changes in density, temperature, and velocity occurring over short distances. These fluctuations arise from the interplay between magnetic forces and thermal motion, creating a constantly shifting environment where stable equilibrium is rarely achieved. Energy transport in this region occurs primarily through radiation and particle motion, rather than convection or conduction in the traditional sense. Photons carry energy outward from deeper layers, while charged particles transport energy through plasma flows. This dual mechanism ensures that energy produced in the solar interior is continuously redistributed into surrounding space. Despite the extreme conditions, this region is not uniform. Variations in magnetic field strength and plasma density create localized structures with distinct physical properties. Some areas exhibit relatively stable magnetic configurations, while others are highly unstable and prone to sudden energetic releases. These variations contribute to the overall complexity of the solar environment. As material moves outward from this inner region, it transitions into the solar corona, where plasma becomes more diffuse but remains highly energetic. This transition is gradual, with no sharp boundary separating the two regions. Instead, physical conditions change continuously, reflecting the interplay between gravitational confinement and outward energy flow. The inner solar environment also plays a crucial role in shaping space weather throughout the solar system. Variations in energy output, magnetic activity, and particle acceleration propagate outward and influence conditions far beyond the Sun itself. These variations are responsible for many of the dynamic processes observed in interplanetary space. In this region, time-dependent processes dominate behavior. The solar environment is never static, with constant changes occurring across multiple scales. Small fluctuations in magnetic field structure can lead to large-scale energetic events, while larger structural changes can influence the entire heliospheric environment. This sensitivity to change defines the dynamic nature of the region. The interaction between radiation plasma and magnetic fields creates a system of continuous feedback. Energy released from magnetic restructuring heats plasma, which in turn influences magnetic field configurations. This feedback loop maintains a state of persistent activity, ensuring that the environment remains in constant motion. As the innermost region of solar influence, this environment represents the origin point for many processes that extend throughout the solar system. The energy and material released here propagate outward, shaping conditions across planetary, interplanetary and heliospheric scales. It is a region where the boundary between matter and energy becomes increasingly fluid, and where the fundamental drivers of solar system dynamics originate. At the deepest visible layers of the solar system structure, the origin of all outward moving energy lies within the Sun's interior, where pressure, temperature and density reach extremes that fundamentally alter the behavior of matter. In this region, hydrogen atoms are compressed so strongly that nuclear fusion becomes possible, allowing lighter elements to merge into heavier ones while releasing vast amounts of energy. This energy is the primary source that drives all activity throughout the solar system, from the solar wind to coronal heating and large-scale magnetic dynamics. The core of the Sun is a region of extreme density where atomic nuclei are packed so closely that collisions occur continuously under conditions of immense gravitational pressure. Temperatures reach levels high enough to overcome the natural repulsion between positively charged nuclei, allowing fusion reactions to proceed. In these reactions, hydrogen nuclei combine through a series of steps to form helium-releasing energy in the form of gamma radiation and high-energy particles. This energy slowly moves outward through surrounding layers, shaping the structure of the entire star. Above the core lies a region where energy transport occurs primarily through radiation. In this zone, photons produced in the core undergo countless interactions with surrounding particles, being absorbed and re-emitted repeatedly. This process causes energy to take extremely long times to move outward, as photons are constantly redirected through dense material. Despite this slow transport, the cumulative effect is a steady outward flow of energy that eventually reaches the solar surface. Further outward energy transport shifts from radiation to convection. In this region, hot plasma rises while cooler plasma sinks, creating large-scale circulating currents. These convective motions carry energy toward the surface more efficiently than radiation alone. The movement of conductive plasma in this zone also generates the magnetic fields that define much of the Sun's outer activity. The constant motion of charged particles acts like a dynamo, sustaining magnetic structures that extend far into space. The solar surface, known as the photosphere, marks the visible boundary of the Sun. Here temperatures are lower than in deeper layers, but still extremely high compared to planetary environments. The photosphere is not a solid surface, but a thin layer where the Sun becomes transparent to visible light. Energy escaping from this layer forms the sunlight that reaches the solar system, carrying information about processes occurring deep within the star. Above the photosphere, the solar atmosphere expands into the chromosphere, and then into the corona. These layers are shaped by magnetic fields and plasma dynamics, forming a complex transition between the dense interior and the sparse outer environment. Energy from the interior continues to drive activity in these outer layers, sustaining the solar wind and powering energetic events that propagate throughout space. The connection between the solar interior and the outer solar system is continuous and direct. Energy produced in the core travels outward through multiple physical processes, eventually escaping into space as radiation and particle flows. This energy forms the foundation of all solar-driven phenomena, from the steady pressure of the solar wind to sudden bursts of flares and coronal mass ejections. Within this system, nuclear fusion is the fundamental process that defines the Sun's existence. It transforms mass into energy through the conversion of hydrogen into helium, releasing energy, according to fundamental physical principles governing mass-energy equivalence. This process is stable on long timescales, ensuring that the Sun maintains a consistent output of energy over billions of years. The stability of the Sun is maintained by a balance between gravitational collapse and outward pressure generated by fusion reactions. Gravity continuously pulls material inward, while energy produced in the core generates outward pressure that resists collapse. This balance creates a stable configuration that allows the Sun to remain in a steady state over extended periods. Despite this overall stability, the Sun is not static. Its internal processes fluctuate over time, producing variations in magnetic activity, energy output, and surface behavior. These fluctuations propagate outward and influence the entire solar system, contributing to cycles of increased and decreased activity that affect radiation environments and space conditions across all planetary regions. The solar interior therefore represents the ultimate source of all energetic processes within the solar system. Every layer above it, from the corona to interplanetary space, is shaped by the energy generated in this central region. Even distant structures such as the heliosphere and interstellar boundary conditions are influenced by the continuous outflow of solar energy. As energy moves outward from the core to the surface and beyond it, carries with it the imprint of the processes that created it. This energy defines the structure of space, the behavior of plasma, and the radiation environment experienced throughout the solar system. In this way, the interior of the Sun is not isolated, but fundamentally connected to every region beyond it. The solar system, from its outermost boundaries to its innermost core, is therefore governed by a continuous flow of energy, originating in nuclear processes deep within the Sun. This flow shapes all regions described previously, linking distant interstellar boundaries, planetary environments, and interplanetary space into a single interconnected system driven by stellar activity.